Vale, adelante.
Okay, so, well, welcome everybody. Also, if there is anybody in the chat, which I don't see. So it's a pleasure to have here today Alejandro Ayala. So I'm going to say a few words about him. So he studied the PhD in Minnesota, the University of Minnesota, with Larry McLaren. And then in '95, he moved to Urbana-Champaign to work with Gordon Bain. And yeah, since '97, he's in Mexico in the Instituto de Ciencias Nucleares, where he's a professor there. And well, his expertise is QCD and magnetic fields. And he's going to talk today about relaxation time for quark antiquark alignment of the spin and global vorticity and relativistic. So please.
Thank you very much, Laura. Thank you very much, Christina, for the kind invitation. And sorry I came in a day which is not necessarily the seminar day, so I appreciate that you made the time to come. And what I want to talk to you about today is some work which is still in progress, so it's in the preliminary stages, that has to do with matter under extreme conditions, and in particular in the context of relativistic heavy ion collisions. One of the intriguing ingredients that has been recently observed in these kind of collisions is the fact that there are particles which exhibit an unusual polarization that they are observed after these kind of reactions. And the common lore is that these polarizations could be produced by medium-induced interactions. So the question is whether it is true that there is enough time for the medium form in these processes to transfer angular momentum to spin degrees of freedom. So this is the question, why I wanted to look at this problem is precisely because the question is quite natural. Is there enough time for this to happen? And so this is what I'm going to show you today. I'm going to compute the relaxation time for these quarks produced in these kind of collisions to align their spin with the global vorticity which may be produced in these reactions. These are my collaborators, and I have highlighted Jorge, who's the PhD student who's in charge of these calculations. But well, these are other students, colleagues from Mexico. Okay, so this. All right. So I guess I already gave you the brief overview, the brief introduction. But let me just emphasize this is a calculation made in the context of heavy ion collisions, and the main question is whether vorticity can be transferred to quark spin, and in particular how this could be shown as a lambda hyperon polarization in this reaction. And well, I wanted to bring all of this calculation all the way to compute the polarization of these particles. And so we developed with these colleagues a model which requires the knowledge of this intrinsic polarization for which we need this relaxation time. And this is done in the context of a rotating QGP. So what I'll show you today is a pure theoretical calculation of the relaxation time and of the intrinsic polarization. And the novel ingredient is the use of this quark propagator in a rotating environment, which we recently developed in collaboration with some other colleagues. And so the conclusion, I hope it's not a spoiler, but that the relaxation time that we obtain is within the lifetime of the QGP for temperatures and baryon densities close to the transition curve. So these results are encouraging in the sense that it is perhaps the phenomenon that may be behind this observed polarization. So let me see. forward, not backward. Think. So, what happens in a heavy ion collision when we have a non-central collision, mid-central to peripheral collision? What happens is that there is an imbalance in the matter that collides. So here, this is a cartoon, of course, but you can see that in this region here, which sort of takes a chunk of this other colliding nucleus, what remains here is not only a part of the nucleons that collided, but they also rotate. And well, you can see this because there is an imbalance in momentum. If you look at, say, for instance, nucleons that come from this, that came from this nucleus here, the row of nucleons that went through is in balance with the row of nucleons that went through in the other direction. So there is a momentum which is not zero, that depends on the distance from the center of the collision. And so the product, classically speaking, of the distance times the momentum produces an angular momentum. So there is a angular momentum which goes perpendicular to what is called the reaction plane in these collisions. And so the question is, what could be the consequences? Now, this rotation is quantified in terms of a vorticity, or what, an angular momentum, which is rather large. And the question is, are there any observables that can be linked to this large angular momentum? And oops, again. But why is this motivated? And the reason is that there is an effect which is called the Barnett effect nowadays, which is spinning ferromagnet in this case experiences a change of its magnetization when it is put to rotate. So if I put this ferromagnet to rotate, so imagine that you are below the Curie temperature, sorry, above the Curie temperature. So there is. Oh, can I probably make a?
Yeah.
You can make any questions. I don't think that there are stupid questions. Right. Yes. No, the unit of angular momentum is h bar. So if you wish in natural units, this is 1. But angular momentum is given in terms of h bar. So all I'm saying is that in these units, in h bar units, you have this much angular momentum. You can quantify it in terms of product of r times p meters, whatever. But in units of h bar, this is the magnitude. But you can use any other unit. No. It's just the units that I use to quantify. So let me go back again. Some reason this is working, so let me do this. Okay, so this is going up, this is going down. Okay, again. So if you have a ferromagnet in which the magnetic moments of the particles that make it up are randomly oriented, if you put this object to rotate, then you align the strings, and so you create magnetization by this process. So this is the idea behind the phenomenon that we want to study here. So if we put this object to rotate, and originally the spins of the particles that make it up are not aligned, the question is, how long does it take for these spins to align in such a way that we get this kind of Barnett effect? And if these spins align within the lifetime of the object, then we may have the chance that, as we see here, transmit angular momentum to spin degrees of freedom, and therefore this spin degrees of freedom, this alignment of the spin degrees of freedom, could be shown up in the polarization of particles along the direction of the angular velocity that we eventually measure in heavy ion conditions. Yes. True.
It's
a very good question. Let me see if I can come up to that. All right, very good. So just to put the context, the calculation in context, we need to look for a probe which is easy to follow in these reactions. You can imagine that what is produced in these conditions is a mess. And so we need to disentangle what are the species of particles that can be more sensitive to show effects of that polarization. And one of them is the lambda hyperon. The reason is that when produced, this is produced in strong interactions, but then it decays, and it decays within the lifetime of the system. Sorry, not within the lifetime of the system. It decays weakly, sorry. But the weak decay is such a way, it's such that the polarization is mostly oriented along the direction of the proton, which then can be measured. So lambdas decay in neutral particles or charged particles like this, and these have a large branching ratio, so it's a good idea to look for this kind of decays. So although they are not very much produced in these reactions, nevertheless, if we are able to identify them, then we can measure the polarization basically by measuring the angular distribution of the protons and noticing that the polarization follows very much the direction of the proton. So it's a good probe to measure spin properties. And this has been done by the STAR collaboration originally. So this was a paper that made it to the cover of Nature. And this is the excitation function of the polarization of these hyperons. The anti-Lambdas are here in red, and the Lambdas are these other symbols here, these squares. And they did it from top Blick energies, which is 200 GeV per nucleon here, all the way down to 7.7 GeV per nucleon. This was done in the so-called beam energy scan program of STAR, and the lowest energies below this one, or perhaps even including this one, are done in fixed target mode. So you see the trend, both anti-Lambdas, this one's right here, or these Lambdas increase their polarization as the energy of the collision increases. Whereas at large energies, it seems to be suppressed, there's no polarization. There's a significant polarization. This is measured in percentage. So it's the ratio of the number of particles with one to the polarization minus the particles in the opposite, polarized in the opposite direction, divided by the total number. And so you multiply it by percentage, and then you get the percentage of polarization. This is not that large. It's not that all of them are polarized, but it is significant. So it's here 10%. And so you can quantify again what is the angular velocity, and you come up with this very large number. So it is indeed a fluid. You can think of it as a fluid in a certain sense that is really rotating fast. The fastest rotating object that we believe is produced in nature. Now, the story is not that simple because, of course, these measurements were done and they caused a lot of surprise. So this is, again, the calculation of the STAR results. But then the Hades experiment came up with further measurements. They did it in gold at mid-central collisions and also silver on silver here. And they still see this trending, this racing trend for low energy. So you see here the last STAR point here, 7.7 GeV is here, but then for lower energies is still here. So it seems to be not a feature of some systematic uncertainties or something. So it's something that is present there. And again, as Christina was pointing out, if you have a magnetic field, if you could have a magnetic field, so the polarized, if, for instance, you think that the polarization is due to the quark content, and in this case, the strange quark that makes up the lambda of the anti-Lambda, in one case, the magnetic field is parallel to the polarization of the anti-Lambda, and in the case of the lambda is opposite. So there must be some sort of separation of the polarization, which seems to be indicated here. Although the origin of this separation may not be necessarily a magnetic field, as it is shown in this slide, where if you exclude that point at 7.7 GeVs, which is this point here with large uncertainties, then it seems that the stark results for the difference of the polarization between lambda and anti-lambda seem to be consistent with zero. So at least up to or down to these energies, doesn't seem to, there is a polarization, but it doesn't seem to distinguish between lambdas and anti-lambdas. Although it is, of course, a matter of also, this is a little bit of cheating, I think, because they excluded the point where the difference is largest here. But well, that just means that they perhaps don't trust this measurement. But in any case, the Hades experiment has not done a calculation for anti-lambdas. So it is still an open question whether or not there is a difference between lambda and anti-lambda. So let me make a quick summary of these observations. There is an apparent rising trend with lower collision energies, although there are large uncertainties, and the QGP component could be responsible for large energy collisions, say, but at low energies, baryon matter should prevail. And so the polarization could be caused mainly by baryon-dominated processes. So again, it's a trade-off, and this is interesting to disentangle the origin as the energy varies. And if we exclude this measurement, this difference in polarization seems to be zero. So based on these observations, we developed a series of works together with colleagues, a model in which for a peripheral collision, the centermost region, it's called the core, may produce QGP, whereas the outer rim, which is called the corona, may not have QGP, but be mainly dominated by nuclear processes. And so if the number of particles have these two components, then the polarization should show the presence of these two components. And if you write it out like this is the polarization, it's the difference between particles with spin pointing in one direction, say the direction of the transverse plane, minus the opposite spin, dividing by the total, both for lambdas and anti-lambdas. Then you can play a game, just reshuffle terms everywhere. And then you introduce what is called the lambda polarization in the nucleon-dominated processes, and the polarization in the QGP-dominated processes, which we can relate to this symbol here. So just bear with me. Believe me, this is simple algebra. We introduce some parameters which have to do with the abundance in the corona or in the QGP of lambdas and anti-lambdas. And so these parameters show up here. And at the end of the day, the polarization for any of these two, lambdas or anti-lambdas, can be expressed in this way, provided we know the intrinsic polarization. Intrinsic polarization is what we produce in the QGP, is E bar, which is defined as these quantities here. Yes, yes, please. No. Sorry, I should have mentioned that. No. What you do is when you have a QGP, you produce strange particles, strange quarks. And so hyperons are made out of U, Ds, and S, or anti-U, anti-D, anti-S, if it is the anti-lambda. So the point or the assumption here is that the spin of the lambda is going to be carried by the S quark or the anti-S quark. So it's not obvious, but since S and anti-S have to be formed in the collision, whereas U's and D's can be just, present in the sense that their mass is smaller, it is usual to assume that U and D form a diquark to which the S quark comes and combines. So all of the spin properties are made out by the S quark or the anti-S on top of the background of a diquark. Very simple scenario. It's got to be much more complicated than that. But most of the spin of the hyperon, the lambdas, in these ideas, many ideas, that in many calculations along this kind of context, is such that the quark of the spin of the lambda or the anti-lambda is carried by the S quark. That's it. If you produce it in the QGP, then the spin transfers directly to the hadronization process. So if you compute how the spin of the quark aligns with the vorticity, with the angular momentum, then that would be enough in this simple-minded scenario to transfer it to the hyperons produced from the QGP. Anti-quark with zero moment, zero angular momentum. That's an assumption. It is good that you pointed it out. Here, I'm not going to speak about that. That was just an assumption. In fact, I'm not going to speak about this model, but if you want to carry it through and compute things with this model, it is true that we don't question ourselves that. So we just assumed that the S quark carries this. That's a good point. But I'm not going to talk about that. I'm going to talk about how to compute intrinsic polarization for the S quark, not for the lambda. But here, for this model, we just assume that it just carries through. Anyway, so what I'm trying to point out is that there is this factor here, which is this intrinsic polarization in the QGP. And the question is, what is the relevance of that object? And unfortunately, this is not a zero, it's a minus. So it should be a minus. All right, so why is that relevant and related to the subject of this talk? What I want to do is to compute the relaxation time, the time that it takes the system to align the spins with the angular velocity. So imagine that you have a system which consists of n0 original particles at t equals 0. You ask yourself, and these particles, of course, in this case, are quarks which are not polarized. Their spin is distributed randomly. So what is the number of particles that leave that state? In other words, that come to be aligned. It's a function of time. Well, it depends on the relaxation time, and this is a simple formula. So the number of particles that come into the state of being polarized is 1 minus this. So if you started with n0 non-polarized, the polarized ones will be 1 minus, sorry, this symbol, minus this expression. So you see that the factor is really the intrinsic global polarization. So what we need to know is this tau. If this tau is smaller than the lifetime of the QGP, then this exponential factor is going to be small. So if tau is larger, so this is no, sorry, the other way around. If the lifetime of the QGP is larger than tau, then this ratio is going to be large, and so the exponential is not that important. So -1 minus that exponential is close to 1, so particles will be polarized. So in other words, given enough time, if we know what this tau is, if the QGP lives longer than that, then we have the chance to transfer the polarization from a non-polarized system to a polarized one. And we will, of course, get more and more polarization as time goes on, if the QGP still lives for a larger than tau time. So this is what we want. Now, like to stop and ask me what I have formulated. And if not, I want to go back and formulate it, because see, the idea is as simple as that. Now it comes a heavy field theoretical calculation, which I'm going to give you some details, but perhaps I don't have enough time, or nor you have patience to follow through all of the results. But is the idea clear? Have I made myself clear? We are few of us, so perhaps we can tell me you're not making sense at all. So I wouldn't get offended. Get it all the time, especially from my students. So again, here comes a heavy theoretical calculation. But what I want to do is to compute how long it takes the spins of S quarks to align with the angular velocity in this system that has angular velocity. There will be consequences for that. It can be that information can be put into models to estimate the polarization of these hyperons, assuming that the hyperon polarization is due exclusively to the that come from the QCD, is due exclusively to the polarization properties of the S quark. Okay, but that's another story. The story I want to tell you today has to do with how do you compute the tau from the quark plasma. And that means at finite temperature and finite baryon density. So this is what I want to do. Okay. Please interrupt me whenever you feel I'm not being clear. All right. So what I have to do to compute that relaxation time goes through two steps. One is the interaction rate of those quarks, which are originally non-polarized, and then interact with the QGP, and the interaction happens through gluons, yeah, which are thermal. So this blob means that the gluons are thermal. And then the quark gets immersed in a rotating environment. So this circle here means that the quark propagator here is carrying the properties of the medium, which is rotating. And so I want to do this computation at finite temperature and baryon density. And it goes through this self-energy diagram, and the imaginary part of this object will give me, which is this imaginary part of sigma, will give me the total rate of interaction if I multiply times the Fermi-Dirac distribution of these quarks. Now, I want both polarizations, because I don't just want to look at particles that have a projection of the spin along the direction of the angular velocity or the opposite. I want both. So these are the spin projection operators. And if I want both, I sum them up. And since the sum of these two guys is 1, the calculation reduces to computing the trace of the imaginary part of this diagram, multiplied by this guy, and then I have the rates, and then I integrate over a space, take the inverse, and that's it. So this is all I want to do. It's rather simple, maybe complicated just because of details, but not much. Why is it complicated, or why could it be complicated? Well, partly because this propagator is a beast which is not easy to handle. So you need to compute that propagator. Yes, then. Sorry. Yes. Yes. It could be. In fact, yes, you're an expert in this, so you know. This is a derivation of the propagator of an object here, which, as you said, could be in the presence of a magnetic field, which is a little bit different than what Schwinger did, but it is equivalent in the physics. Okay. So the derivation is a bit involved, but it's not that complicated at the end. So I want that propagator, and the point is that there is a Green's function, and if I have a differential operator of that Green's function, that would be the equation that satisfies. So the Green's function will be given in terms of this evolution operator. It's called the evolution operator in proper time. So see this way of representing the this object here, in terms of this evolution operator, has to do with, you collect signal up to when you're starting to drive it. And so this operator satisfies this condition from here, provided this, it also satisfies this boundary condition. So this is just things. But see, the point is simple in the sense that if you want to know U and then G, once you know U, then you know G. So what you need is to recall that your solution for U from this equation, you can see that the solution is this one. It involves the operator H in the exponent. And so if you write the delta function in terms of a complete set of functions of this operator, then you apply this operator to this complete set of functions, and so your evolution operator can be written this way. So these are the eigenvalues of that operator. And so you have a way to write the Green's function in terms of those set of solutions. So what I need to do is to solve the problem of a fermion propagating in the rotating environment. And then for that, I need the solutions of the Dirac equation with those conditions. So the next technical step is to find those solutions. And for that, again, it's just doing it, but technically it's not that involved. When you have a rotating system, you may describe this more easily in terms of a metric tensor, which looks like a curved space. So this is the angular velocity. And if I choose cylindrical geometry, this is the way the metric looks there. And from the metric, you can compute the affine connections. Then you can write the Dirac equation under such conditions and solve it. So I solve it in cylindrical coordinates. And what happens is that after a little bit of algebra, you get up here, which is basically so you modify the derivative in the time direction by the introduction of this angular momentum, which is the total angular momentum, times the angular velocity. So for the rest is the same that equation, so you can solve it. And in order to solve it, you first introduce the ansatz, which you sorry, this should have been a plus. You change the sign here, multiply, and then carry through, find these functions. And these are very well known, these are Bessel functions. And well, you just go through and find the solutions for the Dirac equation, and then you're done. Because the propagator for the quarks will be given in terms of this propagator for the Klein-Gordon equation, by going back. And then once you have the solutions, you just apply the formalism that I described, and the closure relation, the completeness relation looks like this. So I can give you all of the details if you're interested. Just I want to go to the consequences. Anyway, so this is the propagator. May look a little bit involved. This matrix, of course, is made out of the external product of the solutions of the Dirac equation, and it looks like this. So you see, seems to be very nice and clean and straightforward and general, but as we know, in these systems, we have lost Lorentz invariance. You see, we have a system which is rotating. We have a preferred direction. So we are used to work in perturbation theory with propagators that can be Fourier transformed. And that only happens if we have Lorentz invariance, so that we go from a difference of positions to a single moment. Now, in this system, which is rotating, well, your orbitals are rotating, but they are moving everywhere. So even more, the system is expanding. So in addition to motion around a fixed axis, you have also particles that move from the center outside. And so the loss, the Lorentz invariance is really lost in this system. So if I want to work in a perturbative calculation, just like the one I show you here with this cartoon, but I need this element here. I need to do a lot of work, and this is what where Christina's comment comes about. Because see, if this was a propagator in the presence of a magnetic field, we also know that all of these physics that I'm telling you about, the fact that we lost Lorentz invariance, is also present. So it's a very involved calculation. It requires to separate the translational invariant piece from the non-translational invariant piece. There's a phase which is called the Schwinger phase. So the same problems appear here. But I want to do a little bit of phenomenology, and in that sense I'm very simple-minded. I'd like to do a first step towards finding a hint that this may make sense. If I find that the relaxation time is way too big compared to the lifetime of the QGP, then there is no hope. There's no reason why I should keep doing this. On the other hand, if I find that the relaxation time is within the life of the QGP, then it may make sense to go ahead and do corrections to the assumption. So in order to work with some reasonable assumptions, what I imagine is that I really have rigid rotation. So I have the spin pointing in a certain direction, and then it starts moving, but I imagine that this is rigid rotation. So if it is rigid rotation, the loss of Lorentz invariance is in the transverse direction of motion around the axis, which is characterized by this angle phi. So if I start at t equals 0 with a given angle phi, I go around like this. I may change the direction of the spin, but if I assume rigid rotation, in other words, that the angle phi changes just as a consequence of the passing of time with the same radius of distance from the center, then that helps me a lot. That allows me to recover Lorentz invariance and write a propagator now in momentum space without having to worry about these other aspects, which are more complicated. Of course, this is an approximation which may be drastic in the sense that since the system may be expanding, then this is not necessarily true, what I'm saying. So in that sense, omega has to be a large energy. In other words, it has to be the one that I just follow, and at least for a couple of cycles, say, imagine that my fermion is really rotating without changing the radial direction. Also, there is one more thing. I didn't speak to you about any boundary conditions in solving the problem. But in reality, we know that we should put in boundary conditions because these are related to causality. So if r is the radius and omega is the angular velocity, we need to satisfy this condition, which means that, of course, there is like a constriction for the value of omega and r. So these two seem to be a little bit contradictory. On the one hand, omega has to be large here. On the other one, omega has to be less than 1 over r. Anyway, so what I'm saying is life is not perfect. So this is what it is. These are the shortcomings of the model, but this is what it is. And let's see what we find within this model. So either omega has to be small and large. There's going to be a window which this works. And let me see if I'm within that window, what we can say. All right. So under those conditions, this equation, which looked a bit ugly, one with this that's here, becomes rather simple from my point of view. So you see, this is the propagator under such conditions. These are the two spin projections. One is weight this way. So these are the usual Dirac gamma matrices. This is the mass of the fermion. This is the angular velocity. You see the energy is displaced. For particles that have their spin pointing in the direction of the angular velocity, you have the energy accordingly. Also, this is for positive charge particles. You get an increase in the energy, and for the others, an increase in the energy. So it has features which are very interesting. So all I need to do now is use this propagator to compute the imaginary part, which, as you can see here, it's just from the poles of the propagator will correspond to positions of T0, which are displaced from the original ones by this angular velocity. So this was some work that we did a couple of years ago. And now the rest of the ingredients, this is something that I shouldn't stop much. But as I said, the difficult part was this one. Now I need to account for this one. And this one is just a gluon in a thermal environment. I will resort to the HDL approximation. And so that gluon can be written this way, say in a covalent gauge. And well, we know what the properties are. So these longitudinal and transverse gluons, these are the functions that go multiplying the longitudinal and transverse projection operators. These are well known. It's a very good question. And the answer is, again, it's very complicated. In other words, you can also do this and put the gluon to rotate, but now the gluon is a spin one particle, and the methodology is similar to what I showed you, but it really gets messy. We try. So, in other words, it's still an open problem. I mean, there are some attempts could be. There you're the expert. I'm not the expert, but it could be very interesting. And again, but in my way of doing things, which I'm saying it's simple-minded things in many senses, I want to, identify what is the important piece in each one of the pieces of the calculation. So the interaction is carried by the gluons. The interaction of these quarks within the QGP is carried by the gluons. So what I want is to put gluons that carry the medium information. I know. But so what is what I want to do? Do I really want a rotating gluon influencing the rotating fermion? So I put rotation in one piece and thermal properties in the other piece. So you can put both thermal and rotating in both pieces, or start building on top of each one of them. So I decided to do this as a first approach, and again, if the results are encouraging, then of course corrections to that can be implemented. But it's a very good observation. So here I don't put the gluons to rotate. I just leave them. Use the HDL approximations for these functions right here. So for that, well, this is the, sorry for this, using the same letter, but this is the gluon thermal mass, which is given in terms of the Casimirs, and for some temperature and finite chemical potentials, these expressions, this is used within these functions here. These are the Jander functions, zero water, logarithms basically. And so this is the calculation of sigma, just that diagram that I showed you. It's QCD in the sense that these are the SU3 matrices here. The propagator that I just showed you how to obtain. These are the effective gluon in the thermal medium. So you need to do the sum over Matsubara frequencies. It's easier if you just single out the Matsubara propagators of these modes. Yes, I'm about to finish. So you do this in terms of the spectral representation. I'm going here quickly, understanding that you are very much familiar with this formalism, so I don't have to stop very much. These are the spectral densities, and then almost the end. So this is the interaction rate. Total interaction rate will be the integral over phase space. We need to integrate over the momentum. The volume, well, it's just a model. If you have two spheres, same radius with a given overlap of an impact parameter, this is the volume that they occupy. Maybe used another formula. And the relaxation time is just the inverse of this objective. So here is the result. I need a relation between the biochemical potential and the energy of the collision and the temperature. And I just use these curves, which are the phase-out curves computed long ago by this reference. So this is for the transition line in the QCD diagram. I need some model for the angular velocity. This is done in several publications. This is one of them. And so you see that as a function of the collision energy, you have this much angular velocity for different impact parameters in these kind of conditions. All right, so these are the results, and then with this I will conclude. So if you look at quarks, say for zero baryon chemical potential or finite, for a given angular velocity and a given impact parameter, this is what we get out of all of these formalism. You see, the transition curve in the phase diagram is around this value, say lower than 150 something. So from here to here, say. So if you look at the mu equals 0 case, the result is on the order of 2 Fermis for the relaxation time. Whereas if you increase the biochemical potential, it becomes even better. So the relaxation time is small compared to the lifetime of the QGP, which is on the order of, say, 10 Gs. 10 Fermis. Good for antiquarks, for which you just have to change the chemical potential. The situation reverses a bit, but still there is a window. Of course, this increases a little bit for the case of chemical potential, which is larger than 0, but still within the lifetime of the system, which again I say is order 10 Fermis. Yes. Yes. Right, absolutely. So what I'm saying is, so you see, these quarks form here. So this is the temperature for the QGP. But since in the calculation, I want to relate chemical potential and temperature in the QCD phase diagram, I use these results in such a way that even, I'm putting myself in the worst case scenario, even if I look at temperatures and biochemical potentials close to the transition line, where the QGP became now hadrons, so to speak, then we still have a good result in the sense that the relaxation time is small. So it doesn't, even in those conditions, it doesn't really take them much to these quarks to align their states. This is the worst case scenario. The best case scenario, of course, is somewhere here. So this need to be all right. So both for quarks and for antiquarks. This, of course, will change with the velocities and impact parameters. It needs to be, but it's there. So let me just conclude. I think my time is about to be up. So the relaxation time in our want to use this to build a model to try to explain the polarization of hadrons. There is this is an essential ingredient, and in this simple-minded field theoretical calculation, we can compute it, and the results are encouraging in the sense that this time seems to be smaller than the lifetime of the QGP. And of course, I still need to explore more consequences for the polarization factor. So thank you very much for the attention.
very similar to propagator, the magnetic for an arbitrary magnetic field of this some over Lambda level, so that I feel that the expression can obtain an analytical response. The case or the final expression.
Yeah, thank you for the question. It allows me to explain a little bit more. Yes, if you follow this technique to find the propagator for a charged particle, either boson or fermion, this is called the Schwinger proper time formalism. And it is identical to the Schwinger proper time formalism. In fact, so much that this parameter here is called the proper time. So if you carry through, it is not necessary to write your propagator in terms of a sum over Landau levels. In fact, both are equivalent. So if you do this exactly, you have the information of all of the Landau levels, all of the Lambda. So now, coming back to this rotating guy, the formalism requires knowing the solutions of the quantum equation that you want, because you see, once you have the solutions to the quantum equation, and this form a complete set, then this function here, the delta function, can be expressed as this product, and therefore, if these are eigenfunctions of this operator, with eigenvalues lambda, then once you apply this operator, what you get is that your function is explicitly given by this expression, but these are the eigenvalues. So now you apply this formalism to this process, in which what you need is now the solution of the quantum equation, well, either the Dirac or the Klein-Gordon equation. So the name of the game is to find phi's and lambdas. And you do. This is a simple problem in this rotating environment, especially if you assume these rigid conditions and no boundary conditions. In other words, you are thinking that R times omega is always less than 1, so you have to restrict yourself to certain values of R and omega. Anyway, doing that, this is the solution, and well, it's there. You can work with it. You lose translational invariance if you allow, or you think that the particles are moving not in rigid rotation, but they can move anyway. But if you assume that omega is large enough, so the approximation is that the motion is basically in the transverse plane. It's just like a classical motion. You see? The angle phi in the azimuth is exactly given by omega times t. Right? So that is the assumption. And if you do that, then this equation, so this thing that could look a little bit messy, can be Fourier transformed. Then you obtain this. But simpler than before. But it's more transparent in terms of the objects that one is used to use in this kind of calculations. For instance, yes, for instance, but it's not, it doesn't come from that. Or it may be that these guys are transiting in quantum levels. This is in that approximation. This may be that. I didn't think of that before. It's a good thing. Thank you. Thank you.